So let's start. So this is welcome. For those who don't know me, I'm Sandrine Thomas. I'm part of the project as a telescope and site scientist. And my co-chair is Dan Scolnic, and he's going to look at questions, as we just mentioned. And this is the room for minimizing systematics. We have, as in other sessions, we have 4 talks. The talks are listed on the right. I'm not necessarily going to read them. I will present them as they go. And I will start with a few reminders that you will probably just hear for this one when you switch. And before I move to that, please mute if you don't talk. And then for the QA, we're gonna, so we have mostly Slack and Zoom, but Dan can only look at Zoom. So if you can, please send them to Zoom as he'll be the one looking at them. So the friendly reminders are the ones you've already heard this morning, and they're about code of conduct. We have a code of conduct, you agree to it. The 3 main points are that we are respecting principle of kindness, trust, respect, diversity, and inclusion. And we want to make sure we provide a learning environment that produces rigor and excellence. Any discriminatory behavior against colleagues on any basis is not tolerated. And if you witness any form of bullying, harassment, or aggression, please report those actions to us. So this is very important. I know you've heard it a lot, but this is extremely important. And also, again, as I mentioned, please mute. All the talks will be recorded. So if you don't want people to hear you or see you, please mute your camera off. And the videos are posted the next day. And also, as a sign of inclusion, please show your appreciation and use thumbs up or claps as we go through those. All right, so I'm done. So the first talk is by Tom Wilson, and he's going to talk about the effect of unresolved contaminant objects on the cross-matching of photometric catalog.
Hey everyone. Yes, so much of the science done with LSST will leverage other data sets to enhance observatory products. This will involve the cross-matching of these data sets where multiple detections are merged into a single object. Oh dear, sorry. We'll merge multiple detections into a single object. However, LSST will be so crowded that traditional cross-matching methods will fail. I can highlight this for the WISE catalog, where I nearest neighbor match to the Gaia data in the black line on this figure. And you see at large separations, false or unrelated matches, and at small separations, a tight distribution of counterparts. However, the official Gaia best neighbor matches say that all matches should be within 1 arcsecond, and as you can see, beyond about 4 arcseconds, all matches are these unrelated matches. So the question becomes, what happens between 1 and 4 arcseconds? And my take-home message is that these matches are also matches where we recover twice as many objects as the official Gaia results. And on the next slide, you will see an explanation for this.
Sorry.
Where bright objects will block out the light from fainter sources, and then these will become blended with this brighter source. So when there is a blended contaminant within these objects, that object will tug on the center of light of the composite object, leading to a larger separation between, in this case, the Gaia and the WISE objects than you would otherwise expect. On the right, you can see that we can model these distributions of these center of light perturbations, and we can combine them with the original Gaussian centroiding uncertainty to produce the general probability that the source has its measured position, which we call the astrometric uncertainty function. And on the next slide, these non-Gaussian tails will increase the separation over which we have to consider potential counterparts. So we can supplement the astrometry of these catalogs with their photometry to break any false match degeneracies that we have in these catalogs. Where essentially, as an ensemble, sources of comparable brightnesses will lie on top of each other in the sky over large areas. However, with this algorithm, we can also include extra information, such as the fact that because we match both photometrically and astrometrically, we can provide users information on things like transience or variability with repeated cross-matches, such as we will have with the time series data from LSST. And because we model these center of light perturbations, we can provide users with information on the relative amount of flux contamination that these objects suffer, and then they can use this information to correct that in their science. So I just leave you with my conclusions at the bottom, but emphasize that WISE is a very useful precursor dataset here because it and LSST suffer the same blending as LSST will do in the future. Thank you.
Thank you. So we'll go to the next talk by Raphael, and this is about multi-wavelength astronomy with Rubin and VISTA imaging.
Hello, yes, my name is Raphael Shirley. I'm working with Manda Banerjee at the University of Southampton. And what we're looking at doing is producing a kind of combined Rubin VISTA imaging product. So VISTA is the visible and infrared survey telescope for astronomy. It's a 4-meter class wide field survey telescope, which is currently taking images with the VIRCam, VISTA infrared camera, which is a 1.65 degree diameter camera, with the broadband filters Z, Y, and JH-KS. So we're sort of, by combining that with Rubin, we're extending into the near infrared. And to do this, we're developing an OBS package. So I think in order to interact with the LSST software pipeline, there's an OBS package for every instrument. So for instance, the OBS Subaru, I think, is the best developed one for the hyperspeed prime cam imaging. And we're trying to process VISTA imaging from the video survey, which is in some of the LSST deep fields. I've got the magnitude limits there on the slide. And it's not comparatively as deep as VISTA, as Rubin LSST imaging is going to be. But by using detections from Rubin and then doing force photometry on VISTA, we can get a lot of extra science from the VISTA imaging. And together with the VISTA Hemisphere survey and others, we essentially have complete coverage of the southern sky. So we will have a product which is a pixel matched imaging product. For every LSST pixel, Rubin pixel, there's going to be a VISTA pixel that will enable us to produce optical and near infrared sort of imaging, as well as catalogues, which might allow us to do science beyond catalog cross-matching, as I mentioned, by using detections from LSST bands and forcing photometry from VISTA and vice versa. As we go to the next slide, please. Thank you. So here we see, this is from Manda Banerjee's 2015 paper, in which she combines DES imaging with VISTA. And what you're seeing there, so the blue dots in the top left, that's DES 5 sigma detections, I think, and then various signal to noise levels, thresholds, the VISTA VHS imaging. And what you're seeing is even at signal to noise of 1, lots of those detections in VISTA correspond to real objects that were detected in DES. I think that sort of shows you the power of this using a different detection band from the deeper survey to force photometry. There's a lot of real objects there, which then can be used to do both fitting SEDs, for instance, to give you the more information that you're going to get from the near infrared. Also, particular kinds of objects which are going to be better detected in near infrared. And if you skip to the final slide, sort of also being shown how these extra bands, JHK, can reduce biasing and errors in photometric redshifts. So yeah, just to summarize, we're doing force photometry from LSST detections and vice versa. This is work that we're just starting. We're going to generate this pixel matched imaging product. And we've got a lot of sort of checks to do in terms of which bands are the best way to do these, which bands we should use. Should we produce LSST, GNR, and VISTA KS, or all band detections? And we're sort of working on diagnostics to decide those issues at the moment. I think, is that about 3 minutes?
Yeah, you're a little over, but that's good. Thank you. All right, the next speaker is Michael Wood-Vasey, and he's going to talk about precipitable water vapor impact on MzLS band legacy survey, Zeropoints and color. I hope I said that right. Go ahead, Michael.
So precipitable water vapor in the atmosphere has an effect on the optical, which is what I care about as an observer, but it also has effects on the radio, to the point that you can use a dual band GPS receiver to measure the time delay from the additional optical path length from water rather than air, and you can measure what that is. the absorption spectrum of of water vapor is actually very complicated, but it's also very well known. And it's an important part of calibrating the full system response function to know what precipitable water vapor is. So in 2015, a team at KPNO installed a dual band GPS system on the WIN 4 meter at my request. And we have compared the results from that, which are also available through a package that my graduate student Daniel Perifort wrote, to provide the precipitable water vapor values in millimeters of water. And we've compared that with the MAL Z-band legacy survey Zeropoints. We haven't explicitly been collaborating with them, although I talked to Arjun Day about this occasionally. We just independently looked at the DR8 data when those came out. And we see a clear correlation actually of two things. So on the left, you see the 0 points as a function of MJD. So there's actually some clear, strong secular trends that are not about precipitable water vapor. Those are the blue points. But in red are the precipitable water vapor points. Oh, I thank you. And you can see that there is a correlation, an inverse correlation, particularly if you look at the central segment. At the very high precipitable water vapor there, that is a very low 0 point. So there's an anti-correlation there in those two. And then the right figure, even without taking out this clear secular trend in the 0 point with MJD, there's a clear trend with precipitable water vapor of what the 0 point is. The color coding is largely telling you about the MJD, so it's largely telling you about the seasons, and the different seasons have this different trend. So if you combine these two things, the MJD dependence and the precipitable water vapor dependence, next slide, you get a prediction for so now we're showing the MJD corrected 0 point, taking out those linear trends in season, and the precipitable water vapor along the line of sight. And there are 3 lines here for 3 different stars, a G2 star, an M4 star, and M9 star. They largely, although not exactly, predict the 0 point dependence on the precipitable water vapor, because that 0 point was determined by taking some reference stars. But we can look at this in a little more detail, and we can ask, well, what's the differential? And let's look at the red stars and the blue stars and the green stars. I made up those color bands, but this is just qualitative. And they vary. So the DR8 had 3 epochs of observation. So we can look at the differential measurement of each star with respect to its average for each of those epochs. So this is actually separate from the 0 point. This is just for each star. What's the differential? And that is strongly correlated with precipitable water vapor, and it's different depending on the color of the star. So then we can compare each of these. Next slide. So then if we compare, for example, the bend of the blue stars minus the red stars as a function of precipitable water vapor, those are not exactly, but roughly that bend behavior, which is the black line. You can fit a simple line to it, or you can fit the red line of the M2 minus K2 of the model for the different stellar colors, stellar types. And so that is well explained. And then just as a brief bit, the reason I care is because of supernova. Because this water absorption line on the right that you're seeing in the gray absorption beats differently against the supernova spectrum shown at redshift 0, 0.5, and 1 as you go through redshift. And it behaves differently for a star than it does for a supernova because a star has a much smoother spectrum. So it's important not just to use some sort of linear correction or something to get the star colors right. It's actually important to say this was from precipitable water vapor, this from water vapor, and get the correct transmission function for that observation. Thank you.
Thank you. All right, so that will be our last flash talk, and it's by Claire Alice Hebert. I should say that. I should know how to say that. Predicting how exposure time affects the Rubin Observatory PSF. So if you can unmute.
Yeah, thanks. Yeah, so my name is Claire. I'll be a 5th year grad student at Stanford, and I'm a member of DESC. So I'll just briefly talk about exposure time and how that affects our PSF for Rubin Observatory. And this affects many science cases, anything that depends on accurately modeling the PSF, whether that's it in one location or across the whole field of view, as is the case for cosmic shear. And when we think about these exposure time dependencies, it's important to note that the dominant contribution to the PSF is the atmosphere. So the question I really want to ask is how does the atmospheric PSF change on these 1 to 60-second timescales? And I'll be using simulations and data to sort of address this question. Simulations are important for developing robust PSF correction algorithms, so we want to make sure that our simulations are robust and realistic. And so part of my work has been on establishing realistic input parameters that include realistic correlations in atmospheric variables. And then I'll briefly talk about some data, some measured PSFs that I'm using to validate these simulations. Next slide. Thanks. So I mentioned that I'm sort of trying to incorporate realistic parameters into the simulations, and I'm taking a data-driven approach. So I'm using global forecasting system outputs from NOAA, paired with wind measurements from Zeropoints, which is the mountaintop of Gemini South nearby. And I don't have time to really talk about how these simulations work, but I'll just highlight the 3 parameters down there in bold that are the ones I've been focusing on, which are turbulence weight, so how you assign how much each layer of turbulence contributes to the overall seeing, and then the wind speed and direction with which these layers move about as you evolve your exposures. So on the right, I summarized some of my results that are available in this GitHub package. And you can see in the right 2 plots, the wind speed and the wind direction as functions of elevation on the y-axis. And so you can see that as you go up in the atmosphere, you have really strong correlations between these wind parameters. And so that's something that's really important to include in the simulations. So for instance, you can see there's a really dominant wind direction, for example. Next slide. And so I've been using these data sets from the Zorro Speckle camera on Gemini South. These are images of single stars, but they have very high temporal and high spatial resolution. So you can see on the movie on the right-hand side, single 60 millisecond exposures, and then the integrated image as you're sort of stacking up this series to a full minute exposure. And as you add these very speckly images that are moving around, your integrated PSF becomes round and smooth. And that's sort of the process that we want to quantify. And those are what the plots on the bottom of the slide are showing. So on the left, you have ellipticity, which is a parameterization of the PSF shape as a function of exposure time for both these data sets that I've been showing and the simulations that I talked about previously. You can see the simulations do fall off more quickly. They sort of become more round, close to 0 by the end of a minute's exposure. And on the right, I am looking at a temporal correlation. So these are looking at a single PSF location and then parameterizing E1 and E2 are components of the PSF shape, how correlated these are from 1/30 seconds to the next. And these are sort of just a brief overview of preliminary results. So thanks.
Thank you. All right, so we're done with the quick presentations, and now I'm going to turn to Dan to the questions.
Great. So I don't see any questions right now in the Zoom chat, but does anyone want to raise their hand?
Oh, I have one in the Slack chat. Then.
Great. Do you want to ask that one?
All right, so it's for Tom. Just move you guys. And we're switching at 11:15. Okay, so we're interested in estimating the atmospheric uncertainty due to the unresolved fainter sources in Rubin data in a crowded field biasing the centroid location of the bright star we do see. Does your software framework already allow exploration of this? Thanks, great.
Unfortunately, no. We actually have the exact opposite thing where we require the LSST and other data set, WISE, Rubin, Roman, pick your other data set. We require them to have as precise as possible astrometric uncertainty, i.e. they have genuinely centroided these things as precisely as possible, because otherwise the Bayesian framework in which we do these cross matches doesn't work, because we have to take these perturbations, or you can add proper motion drifts in there. There's a unknown extra perturbation aspect. You can pick anything, actually. But we would have to convolve that with the original intrinsic Gaussian centroid uncertainty. So we actually require that that's correct, quote unquote, i.e. in the absence of crowding, you would get a distribution that had a Gaussian shape. But what we can do is, because these effects, you see these faint objects in the perturbing of this center of light, you can actually do things where you can see a star even though you wouldn't see it in plain patch of the sky. So I don't know if that's of any use for these faint objects, but because you can essentially see their impact on something even though you wouldn't detect them otherwise, you can kind of back out you can infer their existence. But I don't think that answers your question. And unfortunately, my answer is the opposite to what you were hoping.
Well, actually, first off, if I may respond, thank you very much, by the way, for a great talk. And your answer actually, I think, does kind of address what I was asking, because it's really the uncertainty on the bright objects that we might care about when they're pulled off by the faint ones. But I hadn't appreciated until your answer there that, of course, the method, I think, rises or falls depending on how good that characterization is of the Gaussian for these objects.
If you could go to the second slide, it's this figure on the right is the idea. You take all of your components of what I have dubbed accidentally rederiving. Gaussian used to be called the astrometric error function.
Sure.
Because it was only used in astronomy historically. This astrometric uncertainty function, this idea that you have a source, what's the probability of it being in where you've measured it? You convolve these two and you can just stack any other objects. But yes, you require the Gaussian centroiding uncertainty, this systematic where is this object, even not including the fact that it has been systematically moved, to be correct. Yeah.
Thank you very much. So any field in which you have deeper space-based data, for example, that can be used empirically to see how the ground-based data is being tugged away by those. Yes,
if it weren't for the Gaia data, I would never have discovered this, because Gaia, you can essentially, it gives you a one-sided astrometric uncertainty function. The matches from Gaia to pick a data set only end up describing the other data set because of the high precision with Gaia, which is why you can see, when in the previous figure again, you have this extra tail to these distributions. That's all described by not Gaia.
Yes.
And therefore you can vet your data set by matching it to Gaia is a useful trick.
Okay, well, thank you very much.
Great.
So there's a follow-up question from Michael. Michael, do you want to ask?
Sure. You quoted two space-based data sets. I think you're shot noise dominated, right? So how does that change for significant sky background for a ground-based observatory?
It doesn't. If each of those data sets have done their data reduction, again, I'm going to say correctly because I don't want to tell them what to do. But so long as if they can take data that are bright enough, or that you can assume statistically there are no blended objects, and WISE this is ridiculously bright, but for Hubble or Roman you can probably go a bit fainter, and you cross-match them to another data set such as Gaia, if you get this Gaussian, technically it's a Rayleigh distribution, but you get a Gaussian distribution and you can overplot the quoted astrometric uncertainty and the two lie nicely next to each other. That's what I mean by you have to have the astrometric uncertainty right. With removing all other effects, the uncertainty should be an accurate representation of the precision to which you have centroided this object. Which I don't think that should matter if you're source dominated or background dominated or whatever. As long as you've encoded all of that, your signal to noise ratios are right. You've done, you've got your simplex down the hill modeling, and you've inverted your Hessian or whatever you do. So long as those are as well done as possible, then you should be okay.
Okay. All right. So I have some various questions, but I just want to check if other people want to.
I had a follow-up to that one.
Okay.
Yeah, I was just curious for the centroiding. I imagine it depends quite a bit on the method used to do that. Like if you're doing simultaneous PSF fitting, you'll likely find smaller offsets than if you're doing
the problem
else.
with this is because you have to you have to essentially be able to describe the data fully. It front loads a load of effort on me, quote unquote, whoever is implementing this algorithm, to actually understand that. Because yeah, if you do PSF photometry versus aperture photometry, that will give you a different algorithm for the effect that contaminant objects have versus the centroid uncertainty. But from my point of view, and as I'm trying to implement this, if the astrometric uncertainties as quoted are right, and you understand as the user the subtleties such as aperture versus PSF photometry, you can implement those because there are different algorithms you use to calculate these uncertainty, these perturbations. If aperture photometry, it's just a simple centroid, so you just take the first moment. But if it's PSF photometry, we're planning a new paper to extend the papers that I quoted in the conclusions to describe in more detail how you implement this for full PSF fit models. So it does get very complicated and does require you as the person who is implementing this to understand those. But I am in the process of creating an open source Python package to do this for various combinations of these things. So hopefully that might be enough for your use case.
Cool, that sounds great.
Okay, so I see we have a question from Matthew Temple. So Matthew, do you want to ask this so I can read it off? Okay, I'll just read it. So, here you are. Okay, why don't you go ahead and read it?
Hi, I've got quite a noisy background, so if there's interference, I do apologise. It's a question for Michael on the precipitable water vapour. If that absorption has got a differential profile as a function of wavelength, and is that, if you've got an observation with high PWV and an observation with low PWV, then a change in colour, is that change in colour telling you something about the distribution of flux within each photometric band? And if so, could we use that effect to infer or to aid photometric redshift determination for AGN and galaxies?
Yes. And in more detail, so yeah, so this work I presented is a sort of a condensed summary of a paper we're working on with Ashley Baker at Penn and now Caltech, and then Daniel Perrefort, a grad student at Pitt. But we explicitly have a section actually about AGN, talking about how it matters both, particularly when those lines are of the emission, the redshifted emission lines, that makes a big difference, and in the astrometry. Now, the one detail that's a little harder to figure out is for AGN with significant variability, you're looking at different times anyway. So if you're doing a whole bunch of observations during the night, you have some range of PWV, but you expect that the structure function of the variability of the AGN is pretty low. That actually could work pretty well. If you start comparing over month time scales, we're not clear if the variability of the AGN itself might be actually greater than that. But I talked a little bit with Gordon Richards about this, like it just seems like another thing you should include when using the atmosphere as a prism at Air Mass 5. Also use it as a slightly differential filter to identify that.
Great. Okay, so I have one quick question for Claire. I want to know, is there a characteristic timescale of significant variation in the PSF? So I'm particularly thinking about observing strategy, like if you had two successive exposures of 15 seconds, but some small gap in between compared to a 30-second exposure, is one worse than the other?
I guess that's part of the question that I was trying to answer. And I would say it sort of depends whether you trust the data or the simulations more. And there's some sort of instrumental effects from the data that we're not sure whether they're causing this higher correlation or whether it's actually something that's happening in the atmosphere. So I think sort of to have an answer, my guess is that it would be slightly, 2 15-second exposures separated by some, like a couple of seconds, would be slightly less correlated, but I don't think it would be a significant effect.
Okay. So are we at the time now that we turn over?
think it's been
Oh, it
delayed.
got extended by 15 minutes. So Michael can ask his question that he asked on Slack to Claire, and that's a good follow-up to what you just asked.
Go ahead, Michael.
Do you want to go, Michael, or do you want me to read it?
Oh, yeah, I almost felt like she answered my question, but yeah, it
Yeah,
was just
it's similar. It's very similar, yes.
I was just in the context, right, of this idea of the detailed PSF modeling, effectively, that Tom was talking about. Or, I mean, he wasn't directly talking about it, he was implicitly talking about how that could matter. It'd be interesting to understand the wings of the PSF versus the center, and to generalize this problem of what do you do with around the halos of bright stars? You know, where bright for LSST might mean 17th magnitude and even 18th magnitude. What's the local sky background for that faint star and the wings or something? How do you do that subtraction? What's the knowledge of the PSF? And does that vary? Because I think the challenges we're going to have for the images are estimating the wings of the PSF. You're only going to do for the bright stars. You just don't have the information from the other stars. But you probably both, in terms of not worrying about bright or fat or some other thing, have a much better idea of the core of the PSF from all the other stars. So when you combine that in the data, which do you believe? And do you believe that halo model, I say halo, but I would just mean wings of the PSF, from the bright stars should be applicable to the less bright stars where you don't really have a measurement?
Yeah, that's an interesting question. The data that I have is all pretty bright stars, so I haven't really looked at how that would change. This instrument isn't really built for measuring faint stars since it's taking such short exposures, but that would be an interesting question to look at.
Great. So I wanted the question for Raphael if VISTA has time series information, and what's the plan for that?
So essentially, with VISTA, they're still taking images with VRCAM, but that instrument is going to be replaced with Foremost, the spectroscopic instrument. So there was a time series survey, VAILS, but there won't be any concurrent time series information with Rubin. I don't think. So I think the sort of the photometric redshift product that, if we can contribute to reducing photo-Z biases, that could be very useful for people doing sort of transient science. I know I've been working in supernova science recently, and the sort of the photo-Zs have been, in a sense, the most important aspect of our trying to find interesting objects for follow-up. So I suppose that's where it would contribute most, I think, in contributing to the photo-Zs. But yeah, not any transient factory concurrently with Rubin.
Okay. Other questions that people have?
There was one more on the Slack channel from Will to Tom, if you want to ask your question, or I can read it if you want.
Sure, I can ask the question, thanks. Just kind of a follow-up to Tom. Have you investigated the case where the external investigator gets their uncertainties wrong? Like if they think it's, I don't know, X milliarc second uncertainty, actually it's 2X. I guess that might be hard to notice, but I'm just curious if you've investigated the effect that
Yes,
the incorrect astrometric error has.
My thesis has a whole bit on the APAS data didn't really provide, being it's an amateur survey with the data I was using were quite early stages, and they just didn't have the processing power to do more formal statistical analysis on their products. So I ended up having to bootstrap that, which you can do because certainly this perturbation component has no fit parameters. Unfortunately, I couldn't fit in my 3 minutes a figure of the model overlaying the data with 0 fit parameters. It's quite spectacular, actually, when I saw it for the first time. Fits very nicely. Universe explains itself. It's quite majestic. So you could, if you believed that the perturbation AUF or perhaps your proper motion drifts, which you can again just if you have a model of that you believe, you can bootstrap fit the Gaussian component, convolve them, minimize the model minus data residuals. So you can do that, and yes, I had to verify this for WISE, 2MASS, IFAS, APAS. I did a whole bunch of them in the end for the thesis. And yeah, it's not too complicated, but again, it's just involved. This problem is, I keep sort of giving similar talks on this and going to people, and then they sort of ask for, what's the take home? What do I do? And I'm like, well, you think about your data, and you need to be able to interpret them. And I don't get to just give people a nice, simple, clean instruction. I have to tell them to think about their results. So yeah, but you can fit for your uncertainties if you didn't trust them.
Yeah, thank you. I hope your thesis becomes available so I can read it.
It is available, but to be honest, most of it, minus that bit, is available in the 3 papers that I link. Those the 3 Wilson and Naylor papers. Most of it ended up in paper form. That might be the odd bit that you're interested in, but yeah, it is available through the University of Exeter's open source, the ORE, as they call it. So it's available through that.
I will look at that. Thank you very much.
Okay. Other questions that people have?
Well, if I could just follow up with an answer, I posted a figure for Matt about the quasar dependence in the Slack channel.
Michael, can I ask one to you, which is, what does when you change the transmission functions, what does that change look like?
Sorry, say that again?
So you'll change what the transmission functions to account for the impact of the water vapor. It kind of what parametric form does that look like? Like how will the filter functions look like before versus after?
Oh, I mean, you will multiply you include the precipitable water vapor as part of the system transmission function.
So that's just like an efficiency curve with.
Right. Okay. The simple answer is yes. That's just an efficiency curve. It's a little more complicated in that the resolution of those lines is actually really, really thin. However, luckily the supernova features are very wide. Right, so even quoting that this is the transmission within a 10 angstrom bin severely under-resolves the complexity of the H2O lines. But there are no supernova features that have anything like that, so it's basically fine to just be sampling that. Is this, was that sort of your question, or what?
Yeah, that's close. I might follow up with you offline. Okay.
So I actually have another question from Alison Rose. I can ask, or you can ask Alison if you want to. I am not hearing her, so she might be muted. But it would be interesting to list all the things that can produce systematic error. And that's kind of a question for any of the speakers. To brainstorm about that, and not everyone is familiar with what we're looking for when we talk about Rubin. So if you want to take that on for like 5 minutes before we have to switch. I mean, for example, the ones I'm thinking of are optical signature of the system, but maybe the speakers want to go a little deeper in there.
I guess I just say that the focus on the precipitable water vapor is, for type 1a supernova cosmology, we really care about the per image calibration in a way that you don't if you just want to get the overall stellar colors right. So if you do like a 10-year calibration of billions of observations, I mean, tens of billions of observations, you could back out and fit functions to figure out all the different transmission and absorption stuff, but only with some resolution. And I think it's important to actually get what the precipitable water vapor is directly. the real answer, you should do it both from the stars, and then you should do it from a monitoring station. One of the principles of the GPS system is pretty cheap. It varies in pricing, but 10 to 20,000 for like really nice and no discounts. And it just sits there and runs. And it's next to your meteorology station. So yeah, if it gets hit by lightning, you got to go fix that. But it just sits there. And I think it'd be a useful complement to the other calibration measures, particularly on a per image basis, to understand what's going on. And particularly to understand if there's something happening to the CCD or the sensitivity, or if it's just that, you know, the perceptible water vapor had that impact on the image.
Claire's talk is talking about a lot of those atmospherical signature, right? I mean, we can average them, but then we have in the PSF, looking at the photovoltaics and electricity, we can actually infer some of the systematic flow from the system. Do you want to say anything about that, or are you really focusing on the atmosphere more than the optical signature?
I've really been focusing on the atmosphere, but there is an interesting interplay, and I think if you look at like donuts and things, you can use short exposures to look at the optics, and yeah.
I mean, yeah, the PSF is definitely important for the work I talked about as well, where you wouldn't get these uncertainties correct without the PSF being correct, but you also have to understand what the universe is going to look like in the first place to get, you know, differential source counts in terms of both stars in the Milky Way and extragalactic sources, you know, differential extinction. All you need to basically know what you've taken a picture of to get out the answer for the thing you're fitting in that picture. So yeah, the PSF is very important to this work as well.
Hopefully that answers a little bit of Alison's questions. We can talk for hours about systematics. I mean, there's calibrations of the photometric transmission and other things. But I think for the sake of time, it's 12. Is there any other question that you want to pose to ask? No, we can start migrating to another room if you want to. All right, well, thank you very much to the speakers and to the participants to ask questions, and enjoy the next talks. Thank you.
Thank you all very much.
So I cannot seem to be able to clap, so I'm just clapping.
Oh yeah, hosts get all their stuff turned off. It's really silly.
What's the schedule of this session? So I thought it was 10:30 to 11:30.
So a lot of the session, we actually ended up starting on time, but other sessions did not. So they moved it by 15 minutes to accommodate for the technical issues.
That makes sense.
Sorry.
I think the model of an owner going through and setting up posts is a fragile one.
Yeah, we got lucky. I got in quickly.
This would otherwise have gone too perfectly, wouldn't it? Because nothing's really suffered so far. Couldn't have a flawless conference.
It's going well, so yeah. So this one will end at 45. So we'll have a shorter break. And I'm sorry, Raphael, I didn't have your name on the slide. So I blanked out for a second. So I apologize. I wrote it down this time and I know it. So I apologize.
No, don't worry about it.
All right, so let's maybe wait for a couple of minutes so people will have time to transition.
Robert.
Sandrine. No, it's Alison. Hi, Alison.
Alison. Nice to see you. Are you moving to this session? I'm going to the camera session.
I went to the camera session. I did my duty.
Good for you. I mean, it's so hard to choose, but I thought because I'd spent a fair amount of time in the camera lab, I would go to the camera.
No, well, have fun. I can give you lots of nasty questions to ask, but I won't because I'm on my best behavior.
Oh, please do. You must tell me, you know, just to educate me.
No, there are no nasty questions. There are some obvious questions for information, but that's what you go to the session for.
Okay, so I'm going to go there now. Nice to see you. Are there social activities?
Oh, I don't know. We had one last night for John's birthday.
John Parenko?
Swinbank.
John Swinbank. Oh, nice.
He had a very fancy cake. That's all I know.
All right.
Sandrine wants us to shut us up and get us to work.
I'm going to leave. Bye. Nice to see you.
Bye.
Too.
Thank you, Alison.
Yeah.
Yes. Maybe 30 more seconds, and then we can start. Oh. Okay. I don't see a lot of people joining in anymore. So let's start. So welcome and thank you for joining this session on minimizing systematics. I will be mostly going through the slides, and Dan Scolnic will be monitoring the Slack channel for questions. So please, if you have any questions, use those tools. Just a note though, he actually does not have access to the Slack, so use Zoom instead. Sorry, if you can. If not, that's fine. I will be the one looking at the Slack channel. All right, so we're here we have 4 different discussions from 4 different people. I won't go listing you have the title here, and I will go through the titles when I present each talk. And I will actually skip through the reminder slides, but please keep those in mind about code of conduct and also about the video recording. So we can actually jump in and start with Tom Wilson, who will discuss the effect of unresolved contaminant objects on the cross-matching of photometric catalog.
Okay. Hi, everyone. Yeah, so I'll be talking about that, as said. There we go. So yeah, LSST, much of the science being done with LSST will involve leveraging other data sets to enhance observatory products. And this will involve the cross-matching of these 2 data sets where multiple detections are merged into a single object. However, LSST will be so crowded that traditional matching methods will fail, he says dramatically. To highlight this, I have the WISE dataset, which I have cross-matched in a nearest neighbor fashion to the Gaia data shown in this black line here, where at large separations, we have false or unrelated matches between the 2 objects and a tight distribution of counterparts at small separations. However, the Gaia best neighbor matches all say that counterparts should be within 1 arcsecond, whereas beyond about 4 arcseconds, we can see that all matches are false matches. So then the question is, what happens between 1 and 4 arcseconds? 1 and 4 arcseconds. And my take-home message now is that these are also matches, and we recover twice as many matches as the official Gaia-wise matches do. And on the next slide, you will see the explanation for these missing matches, where on the left-hand side, you see that bright objects block the light from faint objects in the surveys that are near them, and they become blended with the brighter object. And these blended contaminants tug on the center of light of the brighter object, leading to a perturbation in the measured Ys, in this case position, and a difference in the Gaia-wise separation than you would otherwise expect. We can model this distribution, as you see on the right, and getting a statistical distribution of these center of light perturbations, we can combine this with the original Gaussian centroid uncertainty to get a new general probability that the source is in its measured position, which we call the astrometric uncertainty function. And if you go to the next slide, these non-Gaussian tails to the astrometric uncertainty function lead to having to consider counterparts over a larger separation than you would previously. So to break these extra potential false match degeneracies, we can supplement the astrometry from these catalogues with the photometry, where the general idea is that as an ensemble, objects of comparable brightnesses in these two catalogues lie on top of each other in the sky across large areas. However, this new algorithm provides multiple metrics that might be of use to users. The first of which is, because we match both photometrically and astrometrically, we can provide information to users about things like transient events or variability across multiple cross matches through time, as LSST will be able to provide. And because we model the center of light perturbations of these sources, we can also inform users about the level of flux contamination that these objects will suffer. And I just want to finish with my conclusions at the bottom there and point out that WISE is an interesting precursor dataset to LSST because both WISE and LSST will suffer similar levels of blending. Thank you for listening.
Hello, my name is Raphael Shirley. I'm a postdoc at the University of Southampton. I've just started a project working with Manda Banerjee to produce a joint VISTA and Rubin imaging data product and also catalogues. You can see the screen there. So we're developing an OBS package for the VISTA VirCam camera. VISTA, if you don't know, is a 4-meter class wide field survey telescope in Chile. It's imaged essentially the entire southern sky. In particular, I'm concentrating on the video VISTA Deep Extragalactic Observation Survey, which covers the LSST deep fields and also the VHS VISTA Hemisphere Survey, which together with video and some other VISTA surveys covers the whole sky, as I said. And the aim is to produce a pixel-matched imaging product, i.e. for every sort of deep coad LSST pixel, there's a corresponding VISTA pixel in one of the broadband filters, ZY, JH, and KS. Depending on the area, we may or may not have all of those broadband filters. If you skip to the next page, you should see there. So this is a paper from 2015 by Manda Banerjee, which is comparing DES, Dark Energy Survey, 5 sigma detections in one of the deep fields to the VHS, the Wide Area Survey, and VISTA, and just showing that for various signal to noise thresholds from 10 to even 1, actually, you're seeing a lot of true objects detected in the VHS imaging corresponding to the DES detections. What that shows you is that by using this very deep Rubin LSST imaging we're going to have, we can extract real objects from the VISTA imaging that would perhaps be signal to noise 1 sigma detections that we wouldn't include in a catalogue, but we can be sure with the extra depth provided by LSST. And of course, like a lot of people, our plan is to sort of, as a test, run on the current Hypersea Prime Cam imaging, the idea being to have that product ready within 3 years, ready to run as soon as the LSST starts. And if you skip to the final slide, and you'll see here, of course, from the extra information you're getting from these near-infrared JHKS bands, this paper from 2017, Gomez et al. Is showing that can reduce photometric redshift bias and errors. We've got a lot of things to discover, for instance, which of the detection bands we should use. Should we produce a kind of LSST GR VISTA KS band product? Should we detect in every band? Lots of questions like that, and how we build the metrics to make those decisions is something that we're just starting to look at. And yeah, very keen to have help from the community on building this OBS VISTA package. I think it's around 3 minutes. Thanks very much.
And apologies, I could not find my mute button. So thank you for starting. I'm learning how to be a host. All right, so thank you. The next talk is by Michael Wood-Vasey, and he's going to talk about the precipitable water vapor impact on the Mayo Z-band legacy survey, 0 points on color. Go ahead.
All right, here are just a few thoughts from a paper I'm working on with Ashley Baker and Daniel Parafort. Precipitable water vapor has a complex absorption profile, but also very well known. And if you know the amount of water you are looking for, you can compute the transmission that you would get through that very, very well. So we took a look at the Mayo Z-band legacy survey, where in DR8 they published multiple epochs of observations. And we find that there's a clear, interesting secular component that you see in the lower left, meaning just with time. I've actually checked, this isn't clearly associated with any cleaning schedules. I don't fully know what's going on. But if you can do a little visual arithmetic in your head and take out some linear correlations, you see that there's also an anti-correlation between the blue, the 0 points, and the red, which is the measured precipitable water vapor from a dual band GPS system that some people at KPNO kindly installed for me in 2015. And you can see in particular some of the very high excursions in precipitable water vapor have significant dramatic impacts in the Z-band 0 points. All right, and then on the right, you say even if you don't take out those MJD trends, there's still a clear correlation between the 0 point and precipitable water vapor. The color coding is date, and so the green block and the yellow block and the purple block are actually 3 different seasons because we haven't taken out that seasonal correlation you see on the left. Next slide. If you do take out that seasonal correlation, basically just fitting straight lines to each of those MJD versus 0 point things, the residual correlation between that and the line of sight precipitable water vapor is well, although not perfectly, but pretty well explained by the effect that that amount of precipitable water vapor would have on stellar spectra. So here we show the contours are the points from the 0 points from all the images as corrected for the MJD trend versus the precipitable water vapor as measured by the dual band GPS. And the dashed lines are 3 different stellar types, G2, M4, and N9. Within each of that, one of the reasons we finally looked at DR8 is it presented the 3 different epochs of observations from the MzLS. And so we compared the deviation of each star from its average value. So this is 3 numbers, you compare it from the average, so it's only 2 unique numbers, but still. It's clearly a function of precipitable water vapor and of the stellar color. So the points are hard to read, it's red overlaid, blue overlaid around green, but the black lines are the binned versions for blue, green, and red, and then the dashed lines are just lines, straight lines that are fit to that, but will help tell you that the blue stars are a little brighter. The green stars are roughly characteristic of what must be used to use the reference calibration for the MzLS observations, and the red stars are actually notably different. Next slide. So if you compare, basically subtract those lines from each other, but instead subtracting each of the bent points for each of the images, you see here that if you look at the delta Z blue versus delta Z red, there's a clear correlation of precipitable water vapor along the line of sight. So the red points are showing that. The black is the binned. The blue dash is just a simple linear fit. And the red line over the red points, I know that sounds silly when I say it that way, but is an M2 minus K2 star. So it's basically saying if you were calibrating against a K2 star, stars that were M2 would have this effect. So it's not perfect, but it does get the slope right, even though there's that small offset. And then the reason I care is that it's important to actually get the transmission spectrum correct. So it's important to actually take the amount of precipitable water vapor and correct the transmission spectrum, not just to do some color correction to the stars, as the previous 2 plots might imply that you could do. Because if you care about a supernova, which has a spectrum that's much more complicated, it's useful and important to be able to know this. So on the right, you see the precipitable water vapor spectrum in gray, and that's for some nominal absorption amount of precipitable water vapor. Less or more would move that up or down. And it's important to be able to do per epoch, per image calibration of this transmission function. Thank you.
Thank you. All right, and this is our last short flash talk by Claire Hebert, and she's going to talk about predicting how exposure time affects the Rubin Observatory PSF.
Thanks. So my name is Claire. I'm a grad student at Stanford and a member of DESK. And like Sandrine said, I'm going to talk a little bit about exposure time and how that affects the PSF for Rubin Observatory. And this affects almost any science case, since they will depend on either accurately modeling the PSF at one location or across the whole field of view. So for example, cosmic shear really depends on correlations across the focal plane, and so PSF can play a large part in that. And when we talk about how the exposure time affects the PSF, we should remember that the dominant contribution will be the atmosphere. So the question is, how does exposure time affect the atmospheric PSF? And the time scales we're interested in are like sort of 1 to 60-second time scales. And I'll use two things to address this. So one is simulations. And so PSF simulations are important when we develop robust PSF correction algorithms. And in DESK, we're also producing high fidelity image simulations that we use to develop our pipelines. And that's an important input here too. And some of the work I've done in the simulation realm is to improve our input parameters to make them more realistic. So we want to make sure that what we're putting into the simulations is going to reproduce some of these realistic correlations in the atmosphere. And lastly, I'll use some, just briefly talk about some data that I'm using to validate the simulations. Next slide. And so I mentioned that I've been working on simulation inputs, and this is a data-driven approach where I'm using global forecasting system outputs from NOAA and sort of augmenting them with wind measurements from Sarah Bashan. So I don't have time to really describe how the simulation works, but on the right-hand plot is sort of a summary of what this package does, which basically looks at these inputs that I just mentioned, and then produces a set of correlated outputs, so wind speeds and directions, which dictate how the layers of turbulence in our simulation move with time, and turbulence weights, which sort of assigns how the contribution of each layer to the total seeing. And this plot on the right-hand side clearly shows that there's strong correlations in these data as a function of altitude, so it's important to have this realistic input instead of sort of randomly choosing directions for each screen. Next slide. And so the data that I'm using to validate are taken on Gemini South, and they're images of single bright stars with very high temporal and spatial resolution. So this little movie on the right is showing single 60 millisecond exposures throughout a series, and the right-hand panel is the integrated exposure. And so as you add up these very speckly images that are moving around all over the place, your PSF becomes smoother and rounder. And the behavior of this smoothing and rounding with time is sort of what we're interested in. So the two bottom plots show some examples of characterizing the shape as a function of exposure time. So the left is ellipticity, a parameterization of shape for both data and simulation. And we see that the simulation's falling off a lot more quickly. And this is sort of still an ongoing project. I'm not sure yet whether this data is more correlated because of an instrumental effect or whether this is something really happening in the atmosphere. And the right-hand plot is showing PSF shape parameters E1 and E2 from one 30-second exposure versus the next 30-second exposure. So looking at the temporal correlations. So these are just some examples of quantities that we can look at to answer this question of how exposure time affects the PSF. Thanks.
Thank you. So this was the end of the actual presentation, so we can go to questions, and I'm not seeing any on the Zoom, but I see a couple on Slack. One from Robert. Do you want to ask a question, Robert? It's actually on this presentation. So.
I was wondering whether, Claire, you had access to any of the stereo SIDAR data that's been taken. There's some spectacular stuff, I think, from Paranal, resolving the vertical structure of the turbulence sheets. And so instead of resolving the thin shear layers and things like that, Because that's really something like the inputs you need, isn't it?
Yeah, no, I don't have access to this. Do you know when this was taken?
I can find a reference, yeah. It's the Edinburgh group, I think, that does it. Some of the data is spectacular. I mean, it makes you believe in thin layer turbulence theory all over again.
That would be great, thanks.
I'll put it in the Slack channel.
Okay, so there's another one from Tim Lister to Michael. Tim, if you want to unmute to ask a question.
Hello, can people hear me?
Yes, go ahead.
So a question for Michael Wood-Vasey. Part of my question got answered, which is whether it's from dual frequency GPS, which it is. But have you compared it with the products that come from the NASA Aqua and Terra satellites and the MODIS instrument, which also gives precipitable water vapor column measurements?
No, I haven't. Thank you for that reminder. I hadn't been using that instrument because I think it has to be daylight for that instrument, but your point is to calibrate the measurements themselves in the daylight so that you can use it at night?
Yeah, well, I've been looking at using that for sites which don't have the dual frequency GPS, which is most of ours.
Am I wrong? Does it also produce data at night?
I believe it does. You get sort of 2 passes a day.
Great. I mean, so one of the really interesting things that the Apogee survey found, right, which is doing R of 20,000 near infrared spectroscopy, so they're totally nailing the water lines, is that they would go around the sky like this and confirmed as an astronomer, I'm sure the meteorologists knew this, but the astronomers, that the precipitable water vapor really is pretty constant. It doesn't show huge temporal and spatial variabilities, meaning it's less important to get exactly that line of sight. Thanks, Tim. I will take a look at that. So, sorry, you said you were looking at this right now?
Yeah, it's something I've been sort of intimately working on for all of LCO's many sites.
Cool. Thank you.
So I made the comment in the Slack channel, which I thought I might repeat here, but Eli's been doing some nice work on measuring the PWV from looking at delta Z as a function of Z minus Y for stars of known color, which seems to actually work pretty well. It's not surprising that you can recover the variation in PWV without a dual beam GPS, which some people believe the system has fallen apart, and gives you the opportunity for spatial resolution potentially to answer questions like that. So,
oh, sure. Whether or not you want to use FoamyNet is sort of a different kind of thing, but
whether you want to use the spatial variation in the PWV.
Sorry, I thought you meant the system that was used to calculate what the millimeters actually were.
Yeah, that's right. But I mean, my take is that you can do this all in the photometry, which is a self-consistent measurement. You constrain mod trans, then back out the spectra, which is what you need to do for your one way to deal with your supernova problem.
I think you should be able to, and it's probably one of those cases where in year one, it's easier to use the PWV from the GPS, and by year 5, like, you totally know what's going on with all this stuff. Yeah, Eli's plot's very much in my head, and I'm trying to figure that out right now, of like which predicts one better than the other, and then I realized that two things that are correlated, there's not a clear answer to that question.
I think there were more outliers in the PWV measurements, is my memory.
Yeah, there are some, and the PWV doesn't do a good job when it's really dry.
So there was a follow-up question from Melissa on this. What is the time range of the PWV data? I think that's for Michael.
Michael, yeah.
I was still answering the previous question. Can you say that again? Oh, the time range. Yeah. Yes. So this is the time range. Sorry, maybe I don't understand the question.
Is it okay if I talk out loud?
Yeah, go ahead, Melissa, please.
The question was, in the data that you're presenting here, is it mainly the like what years were you looking at for the mile data?
Oh, sure. Yeah. I mean, since I only can translate MJD to season in my head because I was just doing this plot. This is 2016A, basically nothing in 2016B, and then 2017A and 2017B.
Okay. And have you compared that to any of the observatory weather information?
You mean like temperature and humidity and stuff?
Yeah.
Not explicitly. I mean, some of that's folded into the estimate of the PWV. We haven't separately backed out the meteorology. We have that. Yeah, I can totally look at that. Do you have a specific thing you're looking at, or are you?
No. I was. I'm part of Space Watch, so we have a bunch of weather stations up there.
Yeah.
So I was just wondering what kind of correlation you might have with the weather from the satellite data to the actual ground data.
Yeah, they're certainly correlated.
Okay.
Okay, and I have another question for Claire from Morgan Smith. The last plots of simulation versus data are really impressive in terms of elasticity. Have you looked at the size of the PSF, and do you get it as right? Sorry, and do you get it as right? Yeah,
so there's a sort of complicated answer to that, which is in part there's some quality cuts to the data that I use because the postage stamp isn't very big. So if the PSF is too large, then I'm not confident that I can accurately measure the shapes. So I sort of throw out the larger PSFs for that reason on the data side. And then on the simulation side, one of the inputs to the simulation is a seeing value. So depending on what distribution you draw your seeing values from, you will basically be able to tune what size your final PSFs are. So yes, but sort of with that caveat. And right now I'm choosing from the sort of LSST site characterization study.
That would be interesting to see what when we get more data about new surveys of the we look at the DIM and looking at the statistic. Interesting to see how it changes. All right, so yes, thanks. Any other question? We might have time for one more. If not, we're going to thank the speakers again. Thank you very much for joining. And
thank you, everybody.
Thank you a lot. And I cannot clap, so I'm clapping with my hands. Thank you all.
Thank you. Cheers.